This presentation is entitled Slow Your Roll. It says the way to catch a knuckleball is to wait until it stops rolling and then pick it up. It's a famous quote by Bob Euchre. So, the learning goals for this particular presentation is that you'll be able to describe the motion of an object based on a position versus time graph, that you'll be able to calculate the average velocity, and that you'll be able to distinguish between speed, velocity, distance, displacement, and then average versus instantaneous velocity. You should also be able to use the equation v equals delta d over t and a derivative of that, which is uh, delta d equals 1 half vf plus vi t. And you should understand that motion is relative to the observer. So now what we know. We already know that distance, time, and speed are related by the equation s equals d over t. That's an equation that you learned from middle school, and you should be familiar with it as well. Okay, the faster you go, the more distance you cover in the same amount of time. You should also be familiar that distance is measured with a meter stick and time is measured with a stopwatch. Now, in the lab, we actually looked at it and we made a position versus time graph of the ball as it rolled along the floor. Notice how we didn't start timing until the ball actually got to the floor, because before that it was actually changing velocity, and that's the subject of the next presentation. Now the equation v average equals delta d over delta t provides the same information as the slope of the graph. That's what you found, that the slope of a position versus time graph actually gave you the velocity just like the equation. So let's look in a little bit more depth. And we know that time is a measure. It measures the interval between events. It's measured with a photogate or a stopwatch. Generally, we use a photogate for more accurate timing. Generally, we use a stopwatch if we don't need quite the level of accuracy that's provided by a photogate. Now, time is almost always the independent variable whenever it's graphed. And the reason for that is, remember that the independent variable is the one that does not depend on anything else. It's independent, so to speak. And time generally does not depend on anything else. Okay, position doesn't depend on time, or time depend on position. Okay, the time doesn't depend on the position. The position the ball is depends on the time that you allow it to roll. Next, we need to talk a little bit about the difference between distance and displacement. Distance is a total length traveled between two particular points. So if I'm starting right here, if I'm starting right here and I go to here and I do this long kind of circuitous path and I end up here, the total distance is how far my pen moved in order to get to the destination. Whereas the displacement represents the change in position. So it's just, here's I started, here's I finished. What's the shortest point between those 2 points? That right there represents the displacement. So generally speaking, the distance and the displacement can be the same if it's a same straight line path. But generally speaking, the displacement is going to be lower than the distance if there's any amount of turning or curving or anything along those lines. They are both distances, or excuse me, they are both lengths, and they are both measured in meters. Now, we talked about a position versus time graph in the lab, and we said that we determine the velocity by taking the slope. Now, if you look at the slope, we took a graph of position versus time. Well, whenever you take the change in position, so from here to here, the change in position represents the displacement. And then the time from here to here represents the time. So that's how we figured out what the velocity was in the lab, and that's actually the same thing as the formula. Velocity is equal to displacement over time, which is the slope of a position versus time graph. In this one, it says determine the average velocity of the objects based on the graph. So if you were to look at this particular, I'm trying to figure out what the average velocity is. I've got a position versus time graph. It's always important to check what type of graph you have first. And so now I want to find the slope of this particular graph. Now, since this is a straight line, I can choose any 2 points on the graph and it makes no difference. So I'm going to choose the first one because that's an easy point, 0, 0. And then I'm going to choose this point just at random because that's what I want to choose. So my first point is 0, 0. My second point is 8, 8. In order to find the slope, I have to do the change in y over the change in x. And when I do that, the change in y in this case would be 8 minus 0. The change in time, or the change in x, would be 8 minus 0. 8 divided by 8 would give me 1 meter per second. So the slope is 1 and the average velocity is 1. In this next example, it says determine the average velocity between 4 and 5 seconds. So this is one that's a little bit trickier. The reason why is this is clearly a quadratic function. In other words, the velocity is not the same for each second. If you look, there's a curve, not a straight line. So I can't actually use the slope for the entire line, so I have to be more specific. So if you were to look at this, it says determine the average velocity between 4 and 5 seconds. Well, if I'm looking between 4 and 5 seconds, here's 4 seconds, here's 5 seconds. Those are the only 2 points I'm concerned with. The rest of the graph I don't care about. So for these 2 points, I'm trying to find the average velocity, which is represented by a line between those 2 points. So now I just need to find the slope between those 2 points. So I'd say this point right here is, I think it's like 4,16. It looks to be a little bit above 15. And this looked to be 525. So if I'm trying to find the slope, I would do change in y over change in x, or 25 minus 16 over 5 minus 4. Whenever you do that, you get a velocity of 9 meters per second, or a slope of 9. Now if you look, this average slope between 4 and 5 seconds is very different from the slope right here. The slope right here is much, much, much smaller than the slope right here. So what we can say is, in this particular graph, the object is actually increasing its velocity, hence the curve. The average velocity can actually be summed up by this equation right here, which is the average velocity is equal to the displacement divided by the time. The velocity in this equation represents the average velocity, not the velocity at one particular point. So if you were to look right here, if I were to find the average velocity of this whole line, it would be from a line that looks like this. Now, at no point really on the line or on the curve is the velocity at that point. It's slower and it's faster, but it's not really a steady average velocity. So the average velocity doesn't necessarily mean how fast you're going now or 10 minutes ago. So velocity versus speed. You should be able to distinguish between velocity and speed based on the fact that we could tell the difference between position and displacement and distance. They are both measures of how fast you are going. Velocity is a vector, speed is a scalar. They have a couple of other things in common. They are both measured in meters per second as a standard unit. Okay? They're both measures of how fast. They both have what's called a magnitude. A magnitude represents a number. The difference is that a vector, velocity, also includes a direction. Okay? Generally, velocity is smaller. And the reason why is it's calculated as delta d over delta t, whereas speed is calculated as d over t. Now you may be thinking, well, those look like the same. Remember, this is displacement, and this right here is distance. Distance is the total length traveled, whereas displacement is the shortest distance between the start and the stop. Okay, so generally, this is larger. So the average velocity equation we've already introduced you to, but we actually want to go through every variable. We know that V average represents the average velocity. Anytime you see a little subscript right here, it's just defining the original variable. So it's a velocity, and then the little subscript tells us that it's average. So it's together, it's average velocity. Okay, it's the rate of change in position, and it's measured in meters per second. There's lots of different ways you can measure it, and you're really measuring it kind of indirectly. Displacement is delta D, and it's the difference between the final and the initial points. You measure it with a meter stick, and then time is measured with a photo gate or a stopwatch, and it's measured in seconds. So this one says you have a car that's traveling on a long straight road at 20 meters per second for 10 minutes. How far does the car travel during this interval? So if you were to look at this, we've got number, and what we're trying to find. So I'm trying to figure out how far it's going. That's my delta D term. I have the velocity is 20 meters per second, and I have the time of 10 minutes. Now I know I can't deal with 10 minutes because it's in minutes, so I say 1 minute is 60 seconds, and I get a total time of 600 seconds. Now I can actually use the equation. The equation is V equals delta D over delta T, or 20 equals delta D over 600. So when I'm here, what I want to do is I want to isolate this delta D. I want to get this delta D by itself. So what I'm going to do is I'm going to multiply it by 600. In doing so, 600 on the top cancels out with 600 on the bottom. But what I do to one side of the equation, I have to do to the other. So I have 600 times 20, and whenever I do that, I end up with a number of 12,000 equals delta D. And that's 12,000 meters. In the next example, it says you wake up late for school one morning and walk out the door at 8:36 a.m. You travel at an average of 45 miles per hour for the 11-kilometer trip. If school starts at 8:45, will you be on time? So there's a lot of unit conversions that we need to do here, but we have a velocity, 45 miles per hour. Velocity equals 45 miles per hour. So we need to convert that. We'd say 1 hour is 3,600 seconds, and this is the most common conversion that you'll use in this particular unit. And we'd say that 1 mile is 1,600 meters. When we multiply that out, we get a velocity of 20 meters per second. Now, we want to figure out 11 kilometers. Delta D is 11 kilometers. We know we can't deal with kilometers, so we multiply it by 1,000 and we get 11,000 meters. So now that I've done this calculation, I can now solve for the time. And I say V equals delta D over delta T. And I plug in, I say 20 equals 11,000 divided by delta T. In this case, I want to solve for delta T, and a lot of you may be tempted to divide both sides by 11,000. Well, you can't do that, and the reason why you can't do that is that would leave you with 1 over T, and 1 over T is not the same thing as T. For example, if you have the number 2, 2 is not the same thing as 1 over 2. 1 over 2 is 1/2, so that doesn't work. So in this case, you would multiply both sides by delta T, and in doing so, you would get 20 delta T is equal to 11,000. At this point, you can now divide both sides by 20. When you divide both sides by 20, you're left with delta T, and 11,000 divided by 20 gives you a total time of 550 seconds. But that doesn't really answer the question. The question is, will you be on time? And so what you need to do is you need to say, okay, 550 seconds divided by 60 means that it's going to take me about 9.2 minutes. Now, if I leave my house at 8:36, that's 9 minutes to the 8:45 bell. But this is greater than 9 minutes. So since this is greater than the original 9 minutes, no, unfortunately, you're going to be late. Changing velocity. Where does the ball have the greatest change in velocity? And the reason why it has the greatest change in velocity is down the ramp. Okay. When it gets to here, the ball is actually going to continue at a constant velocity. And that's the equation that we've actually been using so far. The equation V average is equal to delta D over delta T represents what we use whenever we're talking about a constant velocity. In other words, the object doesn't change its velocity. It doesn't speed up, it doesn't slow down. But we can actually take the average velocity equation and we can expand it out. We can say, well, when you average something, really what you're doing is you're taking 2 points, or you're taking multiple points, adding all the points together and dividing by the number. Well, if I just take the first point and the last point, I can represent this as 1/2 of the final velocity plus the initial velocity equals delta D over delta T. So it's the same equation. Now, generally speaking, they rearrange this equation to this format right here. This is the more common version of this equation. But you can see where it comes from. It's just taking this and expanding the idea of what it means to be average. And so this is the equation that you use when the object changes velocity. So now, let's see if we can use this equation. And the trick to these equations is the fact that there is 2 velocities. Now it says a car starting from rest. I'm going to go ahead and underline rest for a second. It accelerates to 25 meters per second in 60 meters. How long does it take? Now a lot of you will look at this and say, well, the acceleration is 25, and it's not. It says the car accelerates from rest, accelerates to. This right here are the units for velocity. And so people say, okay, I've got the velocity is 25, and I've got the displacement is 60, and I'm going to solve for t using V equals D over T. And that's incorrect as well. Okay, what you have to realize is that you actually have 2 velocities here. This first term, the rest, actually indicates your initial velocity, what you're starting with. 25 meters per second represents your final velocity. And then you actually have a displacement of 60 meters, and you are trying to solve for the time. When you do this, you know you're going to have to use the form of the equation delta D equals 1 half VF plus VI T. Or, when you plug the numbers in, 60 equals 1 half of 25 plus 0 times T. So now at this point, you need to start to do a little math with it. If you take 25 and add 0 to it, you still end up with 25. But then if you divide it by 2, you get 12 and a half. So this actually simplifies to 12 and a half T. Now you take both sides, and you divide it by 12.5. And when you take 1260 and divide it by 12.5, you're going to get a number pretty close to 5, or 4.8 seconds. The next example says a skateboarder slides down a ramp starting from rest and moving to 10 meters per second in 12 seconds. How far will the skateboarder travel? So in this case, I'm trying to solve for the displacement. I know the initial velocity is 0. I know the final velocity is 10. And I know that the time is 12. I can take it and plug into the equation delta D equals 1 half VF plus VI T. Or I can plug in my numbers. 1 half of 10 plus 0 times 12. Now, 10 plus 0 is in parentheses first. 10 plus 0 is 10. Times a half means 5. Times 12 gives me a total displacement of 60 meters. The last thing we need to cover is the fact that all motion is relative. So an example of that is if you sit perfectly still at your desk, how fast would an observer say you're moving? And it actually depends on where the observer is. For example, if you're sitting at your desk and somebody walks by the room that you're in, you appear to be moving backwards to them, even though they know you're sitting at your desk. If somebody's observing you sitting at your desk from the moon, you appear to be moving very fast because the Earth moves pretty fast relative to the moon. So motion is relative to where you observe something from. And so there is no absolute reference frame. So generally speaking, in this class, we're going to refer to Earth as our reference frame. So in other words, if you're sitting perfectly still, I'm going to say, yes, you are sitting perfectly still relative to the Earth, even though you're spinning as the Earth spins. So we have to pick a point to measure motion from. So you're always going to use the Earth as your reference point unless you hear otherwise. Now, whenever you have relative motion, what that means is velocities can be added or subtracted. The example of this is if you're in a rear-end collision, it's generally speaking not a bad collision if you're both moving. So for example, if this car is moving at 35 miles per hour and this car is moving at 30 miles per hour, because they're moving in the same direction, relative to the two cars, this car is actually only going 5 miles per hour when measured from this car. Because if I'm measuring from this car appears to be motionless. So the other car that's just moving 5 miles per hour faster appears to be approaching me at 5 miles per hour. That's where rear-end collisions are generally minor fender benders. Now, if you're at a stop and somebody slams into you, that's different. But if you're both moving in the same direction, there's usually not a lot of damage in a minor fender bender. Now, a head-on collision is a different story. So if this car is moving at 35 miles per hour and this car is moving at 30 miles per hour, they're actually approaching each other at a faster rate. So the degree to which they're approaching each other is much, much, much higher. So in fact, what you would do is you would add those velocities together. And so the resulting collision would be as if this car were standing still and this car was going 65 miles per hour. So you have to be able to add and subtract velocities depending on the situation. Example of that is this. It says, what is the collision velocity of two cars if they travel at 75 and 65 respectively if it's a head-on collision? And so you would say 75, 65. Because it's a head-on collision, you would add the two together, and the resulting velocity would be 140 miles per hour. That's why head-on collisions, generally involving drunk drivers on a highway, tend to be fatal for the most part or cause serious injuries. In a proficient example, it says, what is the minimum and maximum velocity of a plane that travels at 200 meters per second relative to still air when it encounters a 25 meters per second wind? Okay, so there's a couple of different options that we have here. The wind can come from behind the plane and push it forward. The wind can go from the front and push the plane backward, or it can push from the side. Now, from the side is not going to have as great of an impact as straight behind or straight forward. So I'm going to go ahead and neglect that. We may come back to that in Unit 3, but for now, it's not going to affect the minimum or the maximum value. So I have 25 meters per second. Now, a lot of you say, oh, one's a head-on collision, and one is a collision from behind. You add and subtract. It's not entirely true. If you think about it, a tailwind when you're in a plane is pushing the plane forward, so it's actually making the plane move faster. So in this case, it's going to be 200 plus 25. So the maximum velocity is a tailwind at 225 meters per second. And when you're in a headwind, when something's pushing against you, it's going to subtract. You're going to end up getting 200 minus 25, or 175 meters per second when you have a headwind.